In this video, we're going to do another practice on production planning using linear programming. So here's the question. It's a production planning question. There are two different types of baseball gloves, a regular model and a catcher's model, and they want to know how much or how many of each to produce. For production of these two models, they need operations from three different departments: cutting and sewing, finishing, packaging, and shipping departments. And we have limited capacity, limited number of hours of production time available in each one of these departments. And we also know exactly how many hours of labor in each one of these departments we need per unit of each model, regular and catcher's model. For example, from cutting and sewing department, for producing one regular model, we need 1 hour of cutting and sewing department, 1 hour labor of that department, half an hour of finishing, and 1/8 of packaging and shipping. And we also have the profit per glove, profit per unit of glove for each model, regular and catcher's models. So, and then the objective is to maximize the total profit contribution. And decision here is how much or how many of each model to produce. And then the question asks about the formulation. What is the linear programming model for this problem? It asks for developing a spreadsheet model and the solution, the actual solution. And the rest of the question is about the details of the solution, like the decision variables, the optimal value of objective function, the profit contribution, the left-hand side, the amount of time of production that is scheduled in each department, that is used in each department, and then if there's any slack time in each department. So the first one, what is the linear programming model? That actually asks for the linear formulation, the mathematical formulation. So the way we do it, and I'm going to do it in Excel. I'm not going to write it manually. I'm just going to go here. It's the same. The process is the same. The steps are exactly the same. Decision variables, how many gloves to make. And then there are two decision variables. We have R and C. R for regular model. Let me just add it here. R, number of gloves, or regular model gloves. C, number of catcher's model glove to be produced, right? Decision variables. Let me just. All right, so these are our decision variables. It's a simple problem, only two products, two decision variables. Next step, objective function. An objective function in this case is going to be profit contribution. And we want to maximize it. We want to maximize the profit contribution. But the actual objective function, profit, is equal to 5 is profit, the dollar amount that we get in net profit for each regular model glove. If we make our unit of that, it's going to be, the profit is going to be 5 times R. And then the profit per unit of catcher's model is going to be $8. If we make C unit of that, it's going to be, the total profit is going to be 8 times C. So 5R plus 8C is going to be my profit. And then constraints. So there are different types of constraints that we, there's only 3 constraints. Like I said, it's not really a complicated problem. We have the only type of constraints that we need to consider is going to be the limited number of production time in each department. So constraints, let me just add time used in each department should be less than or equal to time or maximum time available in each department. All right. So the time that is used in each department should be less than or equal to the time that is available. So we can't go beyond that 900 hours in cutting and sewing department, 300 hours in finishing, and I think 100 hours, yes, 100 hours in packaging. So for each one of these, let's say cutting and sewing. So the left-hand side, the time that is used in each department. So for cutting and sewing, we know that this department, how much they need to work. So for each regular model that is produced, they have to work 1 hour. Now, if we make R units, so it's going to be 1 times R plus 3 by 2 or 1.5 hours, they have to work for each catcher's model. So 3 by 2 times C is the amount that they have to work. And this cannot be more than 900 hours because that's the maximum amount of hours. That's the maximum hours available to be spent on production, to be allocated to the production at this department. All right, so cutting and sewing, finishing, packaging, and shipping. So for finishing, half an hour for each unit of R plus 1/3 of an hour for each unit of C, and this should be less than or equal to 300. For packaging and shipping, 1/8 of an hour spent on each regular model, and 1/4 of an hour, 1/4 on each catcher's model. And that cannot be more than 100 hours, the maximum number of hours available in packaging and shipping department. All right. So we took care of everything. And then the only thing is non-negativity. R and C should be greater than and equal to 0. They should both be non-negative. All right. So this is the formulation, the answer to part A, linear formulation, linear programming model. Now let's go ahead and create a spreadsheet model for this. So I'm gonna extend it a little bit to the right. I'm gonna move to the right. We are going to create 2 cells. I'm not gonna write it again, so I can just move it here. So I'm gonna have my decision variables here. R, C, number of regular gloves to be produced, number of catcher's glove to be produced. Objective function, 5 times R plus, remember, in your spreadsheet model, you have to have blank cells for decision variables, and for objective function, you have to have 1 cell, only 1 cell with a formula. that uses the decision variable plus 8 times and a catcher's model. So that's the objective function. And now for the left-hand side, let me just get rid of these. For the constraints, you should have the left-hand side in one cell with formula that uses, again, the decision variable. So it's going to be, the left-hand side is going to be 1 times R plus 1.5 times C, or 3 by 2 times C. All right. If I had my parameters typed, I could have used the sum product function, but that's okay. I'm just gonna type the numbers. Less than or equal to 900. So this is my first constraint for cutting and sewing. All right, left-hand side, the amount, the number of hours, the number of labors used, the number of labor hours used in cutting and sewing department should be less than or equal to 900. So same thing for finishing, half of R, plus 1/3 of C. So 1/3 of C should be, so this is the left-hand side, should be less than or equal, that's the sign. And then the right-hand side is 300. I just typed 300. For the next one, for the next one, 1/8 of R plus 1/4 of C less than or equal to 100. So I have my decision variables, I have the objective function, and I have the constraints, the left-hand side and the right-hand side. All right, so I can go ahead and go to the data tab and go to solver and start putting up the model onto my solver parameters window. So I want to maximize the profit, right? The cell that contains the formula for the profit function, by changing the decision variables, the blank cells assigned to decision variables, representing the decision variables, subject to the left-hand side, the sign, and then the right-hand side. And since they're all, these three, they're all less than or equal, and they're all connected, I can just add them at the same time, okay? So the solving method is going to be simplex LP, and I think that's it. So go ahead and solve it. Let's go ahead and actually get the answer reports. Okay. So yes, so our decision, optimal decision, is going to be to produce 500 units of regular gloves and 150 units of catcher's glove, and this production schedule will lead to a profit contribution of $3,700. $100. And on our department, on our operations side, we are using all the capacity in the finishing and packaging and shipping department, these two. And then we have some slacks on the cutting and sewing because we're using 725 hours from this department, even though we have 900 hours available from cutting and sewing. So these two are the binding constraints, finishing and packaging and shipping. These are the bottlenecks in the process, all right? So now let's just quickly go back to the question. So if we answered part A, this was the answer to part A, the model. The answer to part B was the formulation. We just did that. The spreadsheet model was these cells, like having decision variables, objective function, and decision variables set up in the right format for the solver to be solved. How many of each model should they manufacture? We just answered that. 500 of regulars, 150 of catcher's model. That's the answer to part B. For part C, what is the total profit contribution they can earn with the optimal production quantities? 3,700. How many hours of production time will be scheduled in each department? 725 hours from cutting and sewing, 300 from finishing, 100 hours from packaging and shipping. This is the amount that is going to be scheduled. Which department is going to have slack, or what is the slack time in each department? There's no slack in packaging and shipping. We have 100 hours available. We're using all of it. So there's no slack. Same thing for finishing, but for cutting and sewing, the difference between 900 and 725, which is 175 hours, that's the slack. That's the unused resource that we have from cutting and sewing. And you can check that from your answers report. It's in here, the slack. You can check that from here, the slack. So no slack on the let me just go back here. Finishing, because of the distance here, there's actually a blank cell right to the left-hand side. There's no title here. It actually uses the latest one, which is the actual formula, not the closest one, the closest cell to these, which are the formulas and not the titles. But anyway, so finishing, we already knew it. In finishing and packaging and shipping, there is no slack, but in cutting and sewing, there is 175 units of labor hour, production hours available that is going to be not used. So it's going to be considered as slack.